Hi everybody, this is David Paul, and I'm here with Sherlyn Marlowe. We're going to be talking about ORP Basics today. So I'm sure you're aware Yokogawa is a huge company all over the world, been around since 1915, $3.7 billion company. Interesting because I didn't know this, that active in industrial automation and control, as well as test and measurement and many other business segments. And you can also see that basically in any industrial market that you can think of. So Sherlyn is with Yokogawa. She'll be giving the bulk of the presentation today. I'm with pH-Paul Inc. We've been around for a long time doing training. We train basically in any high-tech water treatment. We have many different formats for training, so if you're interested, you can take a look at our website. We also do technical services. So we have co-hosted with Yokogawa 5 webinars, and this will be over the next month or so. We schedule them for every 2 to 3 weeks, always at the same time. So we did the pH Basics a couple of weeks ago. That's recorded, so you can go to our website and view that if you weren't able to attend. And today we're talking about ORP. So it'll be about a 45-minute presentation. I will give just a very brief intro, and then Sherlyn will do the bulk of the webinar. And then we'll leave 10 to 15 minutes at the end for questions and answers. So just type your questions at any time into the question box. And this presentation will be recorded. You'll be getting an email from us either tomorrow or the next business day. And on that, we'll send you a PDF of this presentation and also the link to go to the recorded webinars, this one and previous one. So just so that you're aware, Yokogawa and pH-Paul Inc. do not have a financial relationship. We're not endorsing or promoting each other's products in this webinar. So we're presenting this webinar just as a service to the water treatment industry. And it certainly is a topic that I find fascinating, as ORP is out there in the industry, and it's one of, I think, the lesser known instruments that we have. So I'm looking forward to this probably as much as you are. So for me, I've been in water treatment, high-tech water treatment, since 1977, and have been around ORP for quite a few years, but there's still a lot to learn. Sherlyn with Yokogawa is a process liquid analyzer product manager. She's been with them for 9 years, has some great experience and also education. At any time, you can input your questions, but we'll cover them at the very end. Any questions that we don't cover, so if we get to the end, it's time to quit and there's still some questions, your questions will be answered by email, and then we'll also add the questions and the answer to the recorded webinar, so that'll still be available after today. So just a real brief introduction to ORP. ORP stands for oxidation reduction potential. We're talking about oxidation or oxidizing. That's where we're taking electrons, and the opposite of that, reduction or reducing, we're donating electrons. So an ORP meter, an ORP measurement will tell us whether a water stream is reducing, it wants to give up electrons, or it's oxidizing, it wants to take electrons. Well, chlorine in water, chlorine is an oxidizing agent. Chlorine wants to take electrons, and it may take those electrons from something we don't want them to take electrons from, like an RO membrane. So important, if we have a chlorinated feed water in front of an RO unit, we have to dechlorinate so that we don't destroy the RO membrane. So one way of doing it, one very common way of doing that, is injecting either sodium bisulfite or sodium metabisulfite, some chemical that will give us a sulfite ion, which is the reducing agent that's going to donate the electrons and give it to the chlorine. Well, drinking water is chlorinated, so this injection of sulfite is to protect the RO unit, and as an on-stream instrument that we can use to make sure that we are completely dechlorinating, we can put an ORP meter downstream of sulfite injection with a feedback to the sulfite injection pump. So if the ORP is getting a little high, then the feedback to the pump will say, pump in some more sulfite. And then typically there's also a shutdown of the RO unit. There'll be an alarm, give you a few minutes to go check things out, and then if the system is still in alarm, then actually shut the RO unit down, again to protect the membrane. So as Sherlyn will go over, we're talking about millivolts plus or minus. It's sometimes a little bit of a challenge with the different waters to find out exactly where zero chlorine is, and most of the time we like to overfeed sulfite so that we are just absolutely sure that we don't have any kind of oxidation of the membrane going on. But sulfite can also, excess sulfite can also cause some biofouling issues. So we want to get zero chlorine, but we want to get zero chlorine and just a little bit of an excess, maybe a 1/2 to 1 part per million of excess sulfite. So sometimes it takes a little bit of trial and error to find the millivolt reading that's exactly right at your plant. So I'm just going to turn this over to Sherlyn now, and she will go through the bulk of this presentation, and then I'll come back and just say a few words when we hit the Q&A section.
Thank you, ladies and gentlemen. Today we're going to talk about the basics of ORP. So we're going to go over a little bit of theory on what is ORP, why do we measure ORP, how do we measure ORP, and then we'll get into the basics of what kind of sensor selection do you need, what are you looking at when you have ORP measurements, and how is it different from your existing pH sensors that you have in your process. And then we're going to focus a little bit on the cleaning and calibration and what our known best practices are. And this is where we've learned the most discrepancies or trying to learn about ORP and actually how to calibrate it come into play. And then we'll talk about some typical known applications. All right, so again, let's jump right into the theory of it. So why do we measure ORP? ORP measurements are less than the pH measurements that you'll have in your plant, but they're going to be anywhere you're going to have some corrosion control, bacterial growth. We've seen them in water disinfection, and we've seen them in like the electroplating when they use cyanide and chromium. The end product is very toxic, and it's the cyanide version that can actually kill us. So we will actually do 2 different ORP to bring it back down so that it's non-toxic form. All right. So what is ORP? ORP is also known as oxidation reduction potential, or another term is called redox. There are 2 different reactions that are happening at the same time. There's an oxidation reaction where something gives up electrons, and there's actually a reduction reaction where something takes those electrons and is reduced. One reaction cannot happen without the other. So something is getting oxidized, something is being reduced. There's an acronym to help kind of remember it, because when we get into this, the terms get kind of confusing and it looks kind of backwards at times. But if we can remember oxidation, oil rig, oxidation is loss, reduction is gain. That'll help us through this. So let's take a look at a real-life example. Let's look at iron and copper sulfide, okay? The first reaction that takes place is actually caused by what we call the oxidizing agent. It happens on the copper. It assumes, it gains 2 electrons from iron, and copper itself is reduced. So this is the reduction reaction, but it's actually caused by the oxidizing agent because it has the capability of oxidizing something else. The second reaction, or what's happening at the exact same time, is what we call the reducing agent. That is actually the iron, because it gives up electrons and itself is oxidized, but it's actually reducing something else. So again, let's look at it a little more clear, because this is where it gets kind of backwards and kind of confusing. Let's get them all up here. Okay, so the oxidation reaction, the item that gives up electrons, causes its overall oxidation number to increase. This is actually what we call the reducing agent. The item, the reduction reaction that happens, where they assume those gain those electrons and its oxidation number decreases, it's reduced, is actually what we call the oxidizing agent. So if we're adding something into the process that we call an oxidizing agent, it's actually causing something in the process to be oxidized. And those reactions generate positive millivolts or negative millivolts between what it is, or which reaction is taking place. So like something that's oxidized generates a positive millivolt, something that's reduced generates a negative millivolt. So let's take another example. Titanium and iron, let's look at sapphire crystals, are actually caused, the blue color is caused by a everyday occurring ORP or redox reaction when natural light passes through the crystals and a reaction between titanium and iron occur, absorb all of the regions of the light spectrum except for the blue. And that's why sapphire crystals give them their actual blue color. So what's similar and what's different about pH and ORP? When you look at it, you're going to use traditionally the exact same reference that you use with pH measurements. You're going to use a silver chloride reference. So any problems that we have with pH, you can expect to have them with ORP. So coating and plugging, they're going to be the same issues and same troublesomes with your ORP measurements. Both pH and ORP are what we call electrochemical measurements. The only difference is, whereas with pH you have a glass, remember that's porous, that has holes, that reacts and measures just to hydrogen. ORP is either going to be, it's going to be a noble metal, either platinum or gold most commonly, and it reacts to anything that is oxidizing or reducing in your process. So it will actually be affected with hydrogen activity going on as well. So sometimes there's applications where if your pH changes, your hydrogen ion concentration changes, you're going to see that in your ORP value as well, and we may have to compensate. So we'll talk about that in a little bit more detail, what we call pH-Compensated ORP. Alrighty, so let's refresh real quick about pH measurements. So pH, we have a scale, goes 0 to 14. You're at 7, you're considered neutral. Remember that this is a 0 millivolt value. Anything below it is considered acidic. Anything above it is considered alkaline. So an acid is defined as something that has substance that's capable of liberating, gives off hydrogen ions. The acidic, or the basic or the alkaline, is capable of absorbing hydrogen ions. So that's what we call, remember, pH is just looking at that hydrogen ion concentration, and it has a scale. We can think of the ORP as the same way. Remember, ORP is characterized by these transfer of these electrons from one atom to another. It's physically going on at the same time. Something is being oxidized, something is being reduced. Something takes those electrons. So we can look at ORP as a similar scale. The normal scale goes from positive 1500 to negative 1500, with 0 being the middle, 7 pH. Anything that is positive, that is what we call the oxidation reaction. That's when it gives the element that's oxidized, gives up its electrons, generates a positive millivolt. Anything below 0, negative, is the reduction reaction, and that's what gives off the negative. Now remember, these are going on at the exact same time. So the value that the analyzer reads is just the overall ability of the process to do one or the other, either oxidate or have an oxidation reaction occur or have a reduction reaction. So we can look at the same way as we do with pH. As we go away from this 0, one direction or the other, we can say they have an increasing either acidity or an increasing alkalinity. The same thing we can do with ORP. But remember, the terms are going to be kind of backwards. If we go positive, we can say it has an increasing reducing capability, meaning we have a lot more oxidation going on that can actually, or oxidizers that can cause reducing reactions. And then the same way, if we have a negative value, we have a lot of reduction reactions going on. So we have a lot of things in the process that are able to oxidize. And I think I just said it backwards on the other side. So let me repeat this. So if we're going positive, these are meaning we have a lot of capability that have the oxidation reactions are occurring. Something is giving up electrons all the time. So we've got a high millivolt positive value. So that means we are actually, as that value increases, we are increasing our reducing capabilities. So we're giving up a lot of electrons to reduce something else. And then again, on the negative side, those are all of the reduction reactions. So as those values go up, we can say that we have a higher capability that we're going to cause something else to be oxidized. We're going to cause something else to be give up electrons so we ourselves can be reduced. And this is where the terms and everything get a little confusing. So just remember, if you're positive, you're an oxidation reaction. If you're negative, you're a you have more capability of causing a reduction reaction. So here's another example of just everyday ORP scales. This is, partial of that scale. Remember, it goes to 1500. But just take a look at bottled water can be around, 2 plus 200 millivolts. Living water can be negative 400. So there is a range within this as well. So what's the actual working principle? Let's look at an example of an acid permanganate solution. We consider this a strongly oxidizing because it strongly attracts electrons from the redox electrode. So the potential is very highly positive. Okay, the opposite would be sulfite. We call this a strongly reducing because it's able to send or push electrons into the electrode. So it's actually a strongly negative reading. Now, the individual that actually defined the calculation that all of the analyzers use to give ORP reading in the, on your display, the millivolt reading, is Nernst. And it's the exact same Nernst equation as with pH, except instead of a pH glass electrode and all the effects of it, you're looking at a noble metal and a process's ability to react or generate a millivoltage on that noble metal. So this is just the overall equation for it. What do we want to look at? With pH, there was a whole bunch of different, and when you get down to the electric circuit of it. Now remember, since we're using the same standard reference electrode, that E3 and E2 voltage, that's the silver chloride pin inside of a KCl, and then the E3 is our junction that's open to the process. Nernst assigned that that combination should be 0 millivolt potential. So then if that's 0, when you look at the whole electric circuit and you sum them all together, your E1 will only be the millivolt voltage that's generated based on your reaction of your ORP system against that noble metal. And again, it's normally gold or platinum. However, with that being said, remember, if that junction gets plugged, a potential is going to generate there and it's going to add to the overall equation. So you're going to build in errors into your ORP measurement, just like you do with pH. So again, you have the exact same problems with that reference as you do the ORP. Now, I mentioned, and obviously you have a solution ground in these as well, just to make sure you get stable reference voltage, because remember, path of least resistance is in through that reference electrode. So any stray noise is going to go through your reference and give errors in your reading as well. So if you have a solution ground and the whole process is grounded, you're going to eliminate the possibility of having grounding or noise interference. Alrighty, so I mentioned briefly that there are some applications, and there's a version of ORP that we call pH-Compensated ORP. What this means processes most commonly in like the cooling towers is where we see it. They also have to constantly change and maintain their pH value. However, if they're looking for, say, like chlorine, availability, that's based on they're looking at their ORP and inferring their chlorine concentration or availability to do something with the chlorine, you will see the millivolt value of your ORP change because they're adding something to change the pH value. So what we do in these is instead of using a reference electrode, standard reference KCl, silver chloride and KCl, we'll actually use a pH measuring glass as the reference. And then that way, as the pH changes, this reference background will ride on top of those changes. So that way it kind of it takes out the interference or the pH millivolt change, and we only know that the millivolt value that's changing is related to the chlorine concentration change in the process. So this is what we call pH compensated ORP. They're not as common as traditional ORP, but there are a lot of applications. Most commonly I've seen it in the cooling towers, but it has been used in beer. Fermentation processes, the tap water, dechlorination, and boiler feed water. We've seen it in there as well. So it can be used, but if you have these, you're not gonna have pH and ORP. You're not gonna have regular pH and pH compensated ORP in the same sensor setup. You're gonna have two independent measurements running side by side each other. So normally that's the level in which the theory that we go. Any deeper than that, it kind of gets a little more complicated than what people actually want. So let's get to what you can benefit from, okay? A traditional ORP loop is exactly like your pH system that you have right now. You have some sort of analyzer, you have some cable, and you either have 2 or 3 individual electrodes, and then they go into some flow fitting normally, or you have it all in one, because some sensors do have the capability of measuring pH and ORP at the same time. However, if we do that and we're in one of those processes that we have to do pH compensated ORP, you don't have the capability of measuring, using your pH measuring glass as a true pH electrode and also a reference at the same time. So we need to make sure that we're choosing the right setup for the right type of application. So again, I said it on the one slide, we've got separate electrodes, we got combined all in one, and then we do have the newer technologies that are coming out, the differential type of reference systems that some of them do have the capability of doing ORP with them as well. So again, just the 12 millimeter, you guys should be aware of or have seen these in the past. They go into some sort of fitting, whether it's directly into a T or it goes into a flow fitting where you with a bypass line. And then the all-in-one. These are common, kind of everybody makes them nowadays. So here's the measuring electrode. Again, most commonly used now is platinum, but there are some applications where a gold will be preferred because there's I guess how do I call it? An effect that can occur that basically, I'm going to refresh my notes real quick so I don't state it wrong, but it has an effect called chemiosorption. I always pronounce it wrong, so I had to pull out my spelling of it. Basically, we're strongly oxidizing solutions. They have oxygen actually bonds to the surface of the noble metal. So in those types of applications that can actually bond with a noble metal, you are kind of essentially same thing, plugging your reference junction. You're plugging your platinum measuring electrode. So in some cases, gold will be beneficial, but normally most manufacturers have standardized on the platinum element. Okay? Typical problems that you're going to see, most common with ORP, are going to just be coating of that platinum metal over time with like buildup of the process, and then obviously over time it will corrode. So if we do have an application that reacts with gold or reacts with the other with platinum, we may need to make sure we have the right metal in the process. I think the same thing goes with any same piping in your plant. This is the biggest one as well. Your reference is traditionally the same pH reference that you have. So any problems, if you have a pH electrode and an ORP electrode in the same line because you just have two different measurements, you're going to have the same problems. So we need to make sure that we have the right junction. We need to make sure we have the right referent, like internal fill solution, and we have proper cleaning going on with it as well. And this is where, remember, we talked about this briefly with the pH. Developers, manufacturers have come out with those different types of junctions with ceramic, there's Teflon, and there's sleeve for the different applications. So if we're measuring ORP in just a general purpose, you know, or like a batch neutralization, you can normally get away with either Teflon or ceramic. But if we're going into really nasty, dirty applications or ultra pure water, you're going to want a sleeve type junction, okay? To get this is just so you can get the longest life out of your electrodes as possible. Same thing, you can either have a single junction, a double junction, or a triple junction. So depending on, again, how long you want to get of life of your probe, because remember, your process attacks your first junction, and then it can go right up and connect your, attack your reference pin. But if you've got a double junction, the process has to get through two different junctions. Same thing, obviously, with a 3. It's got to get through 3 before it can get to your reference electrode. So if we're in ultra pure water, most commonly what you're going to see are what we call flowing type junctions. This means because the process is essentially pure water, there's no ions in there, we need to still make the continuity. So we'll have one that's open to the process that will allow complete continuity to complete that measuring circuit between the ORP electrode and the reference to give our ORP value. In other applications that are more aggressive, this salt bridge, remember this is another one that could be utilized as well as to elongate that life of your reference. So remember, any problems that you have with your pH reference, you're going to have with your ORP reference. So the coating and plugging, we need to make sure we keep it clean. The actual process poisoning the reference element can happen. So that's where getting the double, the triple, or even the salt bridge where you've got the long KCl chamber that has to be poisoned before your reference pin can get poisoned. And then stray currents. Just because it's an ORP, it's a metal measuring something, your reference electrode is still the same. So it's the path of least resistance. So if there's any noise, a pump turns on and it doesn't have good grounding in the pipes, or we're in plastic pipes without proper grounding, you're going to go right up through your reference pin, and it's going to cause drifting in your ORP measurements as well. So we need to make sure that we correct for that as well. And then same thing, if we're in higher temperatures, we want to make sure that internal KCl solution that we choose, or the probe that we pick that has that for higher temperatures, we want to make sure that it is thickened KCl, you know, salt. But for the most time, if you're on like an RO skid, all of those are going to be done through a sample cooler where they're going to be cooled down to room temperature, so it's not necessarily a big problem. So that is the high level of the theory and the selections of electrodes. This is the fun part, the maintenance and calibration. Remember, again, I can't say it enough, but everybody knows that calibrations and validation are different. And if we don't have good cleaning, we're not going to have good calibration. So we just need to make sure that we always start with cleaning them. So here's our known best practices and what we recommend our customers to do for their ORP and how to maintain them. So we always tell you to clean your electrodes first. Use fresh buffer solutions. Never keep ORP calibration solutions more than 2 hours. They're not stable. They can get contaminated very quickly. And then also pick an ORP solution that is closest to your control point, because a lot of times we do just 1-point process cals. I mean, not 1-point process cals, just 1-point calibrations. You can do 2 points, but traditionally, historically, the method's just been a 1-point. So pick one that is closest to your measuring value. And then always allow for stable time, okay? Don't use grab samples if you can avoid it, because if you always grab sample to your process, you're comparing that grab sample to a lab, but you don't actually have a third-party independent to say, was your handheld lab meter that you used accurate? So when we start to drift on, with our online meter, we start to play the who's right, who's wrong. So if we can use known solutions, that's the best practice, okay? And then obviously the frequency is just going to depend on how accurate you want and to your ORP measurement to be. So cleaning, this is what we recommend. You're going to rinse it. Traditionally, you can use HCl, but we've seen that nitric acid actually works better, but you can use methanol, you can use like a Dawn detergent if you've got an oily substance or organics in there that are causing coating. But whatever you use after you clean it, you want to make sure that you soak it for at least 30 minutes prior to actually doing your calibration. And a lot of people don't do this. But if we stick it in something that's really strong, that's actually itself could be considered an oxidizing or a reducing agent, and we've just put all of that on our metal pen, we haven't given our metal platinum time to soak all that off so that it is able to be accurate calibration. So we're building in errors if we don't make sure that we let it soak for a little bit, okay? With us, just with pH, we say if it's within 0.03 pH, you really don't have to calibrate it again. The same thing with ORP. This is where some of the discrepancies come in, is it's really honestly only accurate within a plus or minus 30 millivolt range. So if you're within plus or minus 30 millivolts, you really can just put it back on. You don't have to calibrate unless your SOP says you have to calibrate, then you have to calibrate. There are some times where the processes can be, the platinum pens can be kind of refurbished, for lack of better words. I don't see a lot of people actually doing this, but you can refurbish it with like emery board. You're basically just, anything that was adhered to it, you're kind of scraping it all off. But if you do that, again, just make sure you have enough time for the platinum pen or the gold pen to reacclimate. All right, so common calibration methods. Forgot to take out the little click-throughs, so animation, so give me a moment. So there are two different types of calibration. There's a manual calibration, and it's either a 0, which is a 1-point calibration, or a 2-point, which gives you a 0 and a slope. Traditionally, because it's just a platinum measuring pen, your reference, there's no need to do a slope because there's no pH glass that's being aged that you need to compensate for. So traditionally, we do a 1-point manual cal. You can do a grab sample cal if you want to, but if you do that, we just make sure that obviously anything you do, obviously sample cal is going to be what your process ORP value is, but make sure you again pick a solution that is close to your ORP value, your measuring ORP value. So we just say you're going to clean your probe, you're going to rinse it really well, you're going to make a fresh buffer. This is either done historically with your pH buffer solutions. You mix in some quinhydrone and you allow it to you put a little bit in, stir it in. If it dissolves all the way, you put a little bit more, stir it in. That is traditionally and historically what people have done. Otherwise, you can get pre-made or packets that you can open up, and single-use packets, and make the solution up, okay? But be sure you make them fresh and give plenty of time to stabilize, and then if you do your second point, rinse it thoroughly in between the 2 points. So, like I said, this is most common. Pre-made solutions and quinhydrone solutions are what people traditionally use now. They used to have a light solution mixture, but because of some toxicity to it, it's not good practice to use it anymore, so you don't really see that out in the field there anymore. But basically, with the quinhydrone solution, there's known values out there where if I stick quinhydrone in my 4 and my 7 pH technical buffers that I have, and I use it at a certain temperature, or measure at a certain temperature, that this combination has a known millivolt value. So this is traditionally what people have used in the past. However, more and more people are going to these pre-made solutions. The label here is Hamilton, and that is great and that is fine, and we actually prefer those because with this one, I know it's going to be 475. If it is within its shelf life and if it has been properly maintained, meaning you took a sample, you used it, when you used it, you threw it away, you didn't pour it back in the bottle, so we're not recontaminating it, we know it's going to be 475. So it's a good buffer to go between our lab measurement and our online process when we get into that who's right, who's wrong kind of thing. The thing that people don't understand or what they don't pay attention to is that there's two values on this label. Some of you guys may have already picked it out, but we have to be aware when we use pre-made solutions what the reference background is in it, because this, if I use a probe that has KCl solution, which is what traditionally they are, it's going to be 475. But if I use like the original standard hydrogen electrode, it's going to actually be 680 instead of 475. And this is the biggest common discrepancy that we run into when people say, well, the label says it should be, 300, but I stick it online and it's 270. So what have been developed over time and kind of started to be, or they've been used, are, again, some charts that the different manufacturers over the years have put together that say, okay, if I have an ORP solution that was made from a 1 molar KCl solution, okay, and my electrode that I am using is actually a 3 molar KCl solution, that internal fill solution of that PA or that ORP electrode, I'm not going to read 350 millivolts like this bottle says I should read. I'm actually going to read 372 millivolts because there's a difference just because of the reference in what the ORP solutions were made with and what is in your actual measuring system that you have online. So we run into this a lot when people call and say, I've got a discrepancy. So we just need to know your ORP solution. What is it made with? What's in our probe that we have? Because sometimes if you look, remember the average is within plus or minus 30 millivolts, the discrepancy. If you have a saturated KCl, high temperature ORP probe that should have saturated KCl in it, it could be your 30 millivolt difference right there, okay? So we just need to be aware of this, and there's just educating to, always think about this. It may not be the first thing I come to. I may have to circle back around to it, but quite frequently, this is when we get down to it, this is normally where the discrepancies come. So this you'll have in the handouts when you get it, the ORP quick guide for you guys on, troubleshooting tips for ORP. What we have seen, if you describe what you're seeing as slow responses, this is our recommendations for you guys to what you can look at. It doesn't matter whose equipment, okay? So here I think I've got a little bit of time. I think we're at the 30-minute mark. I'm going to go over some common applications that we have seen, okay? Biocide control is a big one. This is where we actually monitor the ORP value and we relate that back to how much free chlorine is in like the cooling tower is where I've seen it. However, in your cooling tower, you really are also maintaining your pH of your cooling tower. So this is one that we do have to use instead of a traditional reference. We use a pH measuring glass. So we will have actually two independent loops, even if we have a sensor that can measure pH and ORP at the same time. We will have one sensor that's set up with a traditional reference and the pH glass measuring pH, and then we will have the exact same setup with actually using the pH measuring glass as our reference against that noble metal to give us our ORP value. And then this way, whenever I change my pH in my cooling tower, I know that the millivolt value that I'm seeing because of my chlorine concentration is honestly because of the chlorine concentration, not because of a millivolt value associated with the pH change. So again, that chart that we referenced before, this is just common what we've seen. Another one that we have seen ORP is water disinfectants. Similar to biocide control, ORP can be used in the disinfection of the water. It's normally a critical step in minimizing the potential transmission of different pathogens. So studies have been done that determine that if I maintain at a certain ORP value at X amount of time, then certain pathogens are killed off. So we see this in not just drinking water purification systems, but also for like industrial washing machines. They'll use it for disinfection in their water sample there as well. This is one that I've come across in searching with on ORP. I have myself have not seen it, but apparently ORP value is somehow correlated to your ozone concentration in your water samples as well. So this one is one that's out there. I don't know a lot about this one. Like I said, I've just seen it in researching some studies and technical papers that have been written that have been submitted to different chemistry the symposiums and stuff like that. One that is the hot topic, that's been a hot topic for about 3 years now, is this MATS, this mercury and toxic standards. The idea is that if I have a scrubber and I'm measuring pH already normally, but the idea is if I also maintain a certain ORP value, it tells me that I have X amount of mercury that I'm emitting out of my stack. So there are, in the EPA regulations that have come out, again, there are certain values in which the ORP value has to be maintained, and that equals so much mercury that you're outputting. So this is like the biggest hot topic, like I said, for about the past 2 or 3 years. Another one that not as fascinating in the, I guess, necessarily the water treatment world, but you know, indigo dyeing. It's an oxidation reduction. So how long or how strong this reaction goes on will determine how dark our genes are. And then another bigger one, the two most crucial ones that could cause more harm than good, is if we have the electrode plating wastewater plants. We have toxic chromium and toxic cyanide. So these go through a 2-stage ORP reaction that has to happen to reduce the state to the form that we can actually output into our wastewater without causing harm to our environment and ourselves. A couple others that we have here. This is a lot shorter presentation than when it comes to pH, because it's just so new, not new, but less known. We don't want to overpower or like over numb you with just death by PowerPoint. But basically magnesium, refining of copper, silver, nickel, tin, all those are ORP electrodes. And then besides, even in the electroplating applications, besides the chromium and the cyanide reduction within the process itself, they have ORP measurements that they have to maintain the baths, and they have to maintain at certain ORP values for a certain amount of time. So those are the most common that I have seen or found. Like I said, that ozone one was new to me. Over the past 9 years here. So we briefly went over ORP, how to measure it, what kind of common equipment that we're going to have, how is it different than our pH, our best practice for your cleaning and calibrating, and where we see the most discrepancies occur. Hopefully I explained that well enough for you guys. And then typically known applications. So I should be at the 35-minute mark now, so I'm going to open it up for Q&A at this time.
Hi everybody, this is David Paul again. Thank you so much, Sherlyn. Very interesting presentation. So now, if you haven't written your questions to Sherlyn, please do so. And now Sherlyn will be giving a question, so she'll say the question and then give the answer. And we've got about 15 minutes of Q&A. If we run out of questions, then we'll just end. If we have more questions than we can cover, then again, you'll be answered by email, and we'll also put the question and answer on the recorded webinar. So again, here's Sherlyn to answer your questions.
Yeah, and also to add to that, you know, process analyzers is an always changing world in learning. So if I don't know your answer, I will be honest and tell you I actually don't know the answer right now, but I will always find an answer, and I'll get your email from David and them, and we'll make sure that you get an answer within the next week easily. So our first question here is, what is the relation millivolt to ppm? Okay, well, this is going to be dependent on the chemical in which you're referencing. So, like the known chart that I have right now at my hand is for those chlorines, right? So, if you've got an ORP value of about, you know, 800 to 825 millivolt value, that's what's generated on the analyzer display, that would be equivalent to, say, about a 5 to 6, about a 4 to 5 ppm range, if I'm reading this chart correctly. It's a little small, so I have to zoom in on it. So it's going to differ from what we're looking at, but they are value charts out there that we can get. How come in every stream I have the ORP goes up with oxidizers just as the pH potential increases with acidity, where you stated the opposite? And that is actually, I have looked at that multiple times, because every time I go over this, it sounds so backwards. And it actually is that the reducing, the oxidizing agent causes a reduction. I'm not going to say it wrong, so I want to look it up. And I may have put it backwards on the chart. My little cheat sheet of the ORP scale that I made may have been wrong. So that question, Daryl, if you can flag it, I actually want to verify that. But the oxidation agent is actually causing a reduction, which should be a positive value, not a negative value. So I just want to dig into that some more and make sure that what I just stated wasn't wrong. Okay. So we have 0.005 ppm of free chlorine, but 1 ppm of bisulfite. But ORP is reading 350 millivolts. pH is 7. Can you please help explain why we have strong positive ORP reading while the sulfite concentration is much higher than the oxidizer? This is what I was actually kind of concerned about. That's a chemistry question. The details that that one I'll have to get back with you on, because I don't want to state it wrong. ORP topic is a little, it's not new, but from that side of it, I don't want to state wrong. I want to make sure we get you the right answer so I can get the right person in contact with you. Okay. Next question is, should we do calibration on ORP? We have a brand new ORP, and when measuring 200 millivolts, the standard calibration solution, it reads 250. Should we or should we not calibrate? Like I said, we say it's 30 millivolts, so that's outside of that range. So yes, that's 50 millivolts. It would be good practice to calibrate. Another thing I forgot to mention when we were talking about calibration is, if you are using a combination electrode that measures pH and ORP at the same time, and you do a pH calibration, you need to make sure that you check with whoever the electronic supplier is, because I know in our electronics, the 0, the first calibration point that you do that would be associated with your ORP value, your 0 offset, that is in calibrations. So I forgot to mention that, so I just want to mention that here. But for this particular question as well, is yes, make sure you do calibrate that. Okay, I'm looking. Okay, next question here is, what would be the indicated probe for a system measuring ORP in the -300 to -375 range with high chlorides, measuring biological reduction and high chloride solution? There, you're going to need a reference that is at least probably a double junction. For one, if you're going to use traditional reference, but I would be interested if where you are, if you're also going to maybe need to do the pH-compensated ORP to make sure that the millivolt value is due to, well, it says high chlorides. Yeah, so chloride solution, yeah, if you just have a double junction reference electrode, traditional KCl, then that would be okay. Alrighty, next question is, we have two ORP probes with the same manufacturer brain but different models. The two probes read 100 millivolts in difference and highly positive. How do we determine which ORP we should be selecting? This is the fun part because we have to start to isolate them from each other. So we have to look at, okay, if you take your ORP probes, assuming they are easily quick detachable cables, because if I tell you to swap a whole cable, you may get angry and have to not want to run the cable, especially with the long distance. But if you have a quick disconnect, simply swap the probes and see if that one that was 100 millivolts higher than the other one, see if it stayed with the transmitter or if it stayed with the sensor. If it went with the sensor, then I would start to look at that particular sensor that it followed. If it stayed with the transmitter, then we need to look at the age of that transmitter, look at the cable on that transmitter, and see what's going on, because it's probably not the, it's something in the instrumentation that's causing the offset. I have a question about how high of temperature can we go. That question is going to depend on whose sensor that you use. Some sensors can only measure up to 105C, so 221F. Other sensors can go up all the way to 130C, and I think it correlates back to either 280F or maybe it could be 3F. Getting up there, going from Celsius to Fahrenheit, I don't know the calculations off the top of my head. So it depends on the equipment that you have, depending on how high you can go. About how much time should we allow for stabilization time? Depending on if you're in your solution. If you have cleaned it with something that's strongly oxidizing or strongly reducing, that 30-minute window is a good rule of thumb. If you've done that and then you put it in your ORP solution, I would say no more than 2 to 5 minutes is probably what's needed for an ORP electrode, unless we haven't cleaned it. Over that, we're going to probably need to clean it, because these should be a lot quicker calibrations than what we see with pH, because it's just a piece of metal. Can ORP be used in corrosion monitoring program? This is actually something that, yes, it can be done. From my standpoint, I can't tell you what the millivolt value is you're going to have to maintain it at. So someone there somewhere has probably done, some investigation to it. I can tell you that EPRI has done some investigation, but it's not been, far as what I've seen, it's not been finished. They've done it on like copper pipes. They do what they call ECP, electrochemical potential, but all it is using a standard reference, that KCl reference, and instead of a platinum or gold, it's actually using a copper pin. So it's the idea, and its idea is you use a metal pin that is the same process pipe, and then that will corrode away and generate some millivolt value. And if you maintain a certain millivolt value, you get the longest life out of it. So it's an ORP measurement, but they refer to it as ECP. So you may want to look into that if you're looking at what you want more information about corrosion monitoring. Alrighty. Got a question here. What would white powder deposited on an ORP probe indicate? Need more information on where you mean white powder. If you're using a combination electrode and you take the wet boot off of it and there's white powder on the body of the probe, that's just the internal KCl salt solution that has dried out and crystallized, would be my guess. Okay. Next question is, what patterns do you use to calibrate? Not sure what you mean by what patterns do you use to calibrate. Can we get a little more clarification on that question, please? Okay, we'll come back to that one, whoever asked that. If you're asking about patterns as in do I do pH over calibration, that's my recommendation. If you're using a combination and you're measuring both at the same time simultaneously, do the pH calibration first, then do that 1-point ORP calibration. All right, we got a next question here is, do you have any idea about hydrogen peroxide in regard to ORP? Yes, we have history with it, and what more in particular are you asking about? Okay, so next question here is, we have ORP probes with white wet, not hard material coming out of the ORP junction. We think this is messing with our readings. Do you know why this might be happening? Yeah, my guess is it's the KCl solution that's coming from the inside of the probe out, and then it's reacting at the point with your process. Which is more healthy, the water with ORP positive or ORP negative? That one is beyond my knowledge, so that one I would, have to look into for you, and or refer back to someone like David who's got more experience with RO skids and helping evaluate those. Okay. What is the typical ORP range that is desired for protecting RO membranes while minimizing biofouling potential? That is one as well. From where I standpoint, I don't normally tell customers the ranges, so we can find that for you and get that back to you easily, because I'm sure David's group has a lot of experience with what they've seen and what they've helped people with before. Okay, we got one more question here. It says, what is the typical ORP range? Oop, hold on. Give me a second. The chat window just jumped up on me. What is the typical ORP range that is desired for protecting RO membranes while minimizing biofouling potential? Are there types of probes that shouldn't be calibrated? The manufacturer says not to calibrate. Okay, so the first part of this, because it was multiple questions, is the same thing as the previous question. So again, people like David's group have that information that can definitely give you from what they have seen over the years, and where to maintain it good so that you don't have the damage to the membranes. If you have a manufacturer that's telling you that you don't need to calibrate your ORP probe, I think that's honestly a little crazy and ridiculous. If it's my company, please give me a call and let me know so that I can correct my support staff. But you have an ORP that is open to your process. If you don't correct for the plugging and coating that's happening, that yes, you're going to be cleaning it, but if you're not also considering that, you're not going to get accurate readings. So it wouldn't be far off for you to be off, okay? So yes, calibrate. There's one question, this one's the last question, is there's two questions here. I guess they came in late. So are there types of probes that shouldn't be calibrated? Oh, same one. I'm sorry. We just answered that. Last question is there any application for ORP in moisty air to measure certain contaminants? That one would be a new one for me. So I can look at it for you if you want me to do some investigating and ask some of my counterparts if they have seen something similar and get their feedback. I can easily ask around, and see what we can find for you. So there were a few that are outside my knowledge, so I will make sure that we get you answers to those guys.
Thanks, Sherlyn, and thanks everybody for your questions. So we're right here at the end. I'll just mention that you have to do a little trial and error to determine at your plant what the ORP value is going to be, where you get 0 chlorine and just 0.5 to 1 part per million of excess sulfate. So it's not something where we could just tell you an exact millivolt, because it's gonna depend on some things at your plant. So let's just wrap up. Thank you so much for attending. We have lots of different training, and we go over a lot of things like how to come up with the millivolt reading. So if there's anything that we can do for you as far as the training in, we would love to work with you. We also have technical services where we may be of value. So thanks so much for attending. If you wouldn't mind, as you're exiting, there's just 3 polling questions. It really doesn't take any time, but it gives us some feedback on how satisfied you are with this webinar. Thanks so much. See you next one. Bye-bye.